All right, well, welcome everybody. My name is Gopal. I'm a physician scientist here at the Broad Institute, where I work on strategy and operations for machine learning. And I'm also co-founder and co-organizer of Formal Methods for the Informal Engineer. So I wanted to just take a few minutes to say a few general words about the workshop, because I think it's a rather unusual event in terms of the ideas that we're covering, the mix of audiences, and the workshop structure. So in a nutshell, what brings us together today and the vision behind this workshop really is not so much about the present, it's about the future. And I don't think I need to convince anybody in this audience that with the increasingly prominent role that software systems are playing across all of society, we already do have mission and safety critical software systems. Systems that need to be built with extraordinary skill, with a significant amount of effort, taking advantage of the most cutting edge thinking about software and technologies themselves. And as we'll learn during the course of this workshop, achieving mathematical guarantees of correctness for any piece of software is extraordinarily challenging. And so the question is when it's actually worth it. Now, our perspective coming from the Broad Institute really has to do with our history in the genomic space. We've known for several years now that the volume of genomic data production globally is growing exponentially, faster than Moore's Law even. There was an interesting paper written a couple years ago, actually, called Big Data, Astronomical or Genomical? And they predict that by the year 2025, genomic data production will exceed that of astrophysics as well as social media. Now, for those of you who are coming from the life sciences, you probably know that there are actually many other data generation technologies independent of genome sequencing itself, ranging from single-cell RNA sequencing to CRISPR-based assays, to cellular imaging, an entire spectrum of medical imaging modalities. And the net result of this exponential growth of multimodal data generation will be that in the coming decade, I believe we'll see the life sciences and medicine become fundamental drivers of progress in machine learning and AI. And in addition, give rise to an entire ecosystem of software systems, many of which will have to be mission and safety critical. Now, in thinking about this workshop, there's only a couple of us who are coming from a background in the life sciences. And so when we started kicking around some ideas, we decided actually early on to take a step back and view things from a domain agnostic perspective and really just ask some general questions about how one builds highly reliable software in general. When you do need to build a mission critical system, what are the techniques that are available? How does one go about it? And when you ultimately decide to commit to a highly rigorous process of building a system, what is the overhead? And so our perspective in taking this domain agnostic view is really that the purpose of this workshop is to start a conversation. We think that whether it's 3, 5, or 10 years from now, when we ultimately need these solutions, that we'll be able to connect the right people to the right solutions, to the right problems by getting an early start on bridging these rather unlikely communities. So I think I'm the first to admit that it's very unlikely that many of you leave this workshop doing formal proofs left and right, and that's totally okay, it's by design. But what I hope we will have accomplished is to spark some curiosity, plant some intellectual seeds, and most importantly, made some connections, and hopefully jump-started a long-term process where I think we're all going to work together to tackle some incredibly ambitious problems over the coming years and decades. Okay, so let me go ahead and introduce our tutorial leader today. Cody Roux is a mathematician and computer scientist by training with a background in programming language theory and formal methods. And he's currently working as a senior engineer at the Draper laboratory, where he works on high assurance systems. So with that, let me go ahead and turn it over to Cody.
Thanks so much, Gopal. Gopal's doing an excellent job of organizing this, and I'm very excited to be here talking to you. Because, this is my soapbox, I guess, I couldn't help but prepare a couple of slides, which, should be relatively short, and then we can just dive into the technical aspects of the tutorial itself, which, it should be pretty introductory. Today, we're going to talk about the Coq proof and specification language, which is, the name of the system, but also the name of the language. So just to summarize, if you were here yesterday, you saw Phil's excellent talk. It was delightful and breezy. This talk, it is going to be less breezy because of the nature of the system that I'm presenting today. It should still be rewarding, but there are certainly some differences. I think Phil touched on them yesterday, but basically Z3, is really designed to be a very powerful, very complex push button system where you enter questions, you push a button, and you get an answer. Coq is not that, but it is powerful in its own way, and I'll explain a little bit more how they differ in a minute. But first, I'm just going to motivate things a little bit. So I couldn't help. I don't know if any of you grew up in the US in the 90s, but there was this program called DARE, which was kind of a program to make you afraid of taking drugs of any kind. And as I'm sure you all know, it was an incredibly successful program, very effective. And so I'm going to use the same strategy to make you a little bit afraid of computer bugs. I'm sure you all know that programs have bugs and they're pervasive. But I think it's useful to just unpack it a little bit and understand why and what should we be doing? Why should we be taking action, if any? So obligatory XKCD comics. Basically, the point of this comic is just, airline engineers that are like, yes, it's scary, but we really engineer these things well. It's very unlikely that a plane will fall out of the sky. An elevator engineers are, these elevators are foolproof. There's really nothing bad that can happen. Accidents are incredibly rare. And then you ask software engineers about computerized voting, and they're saying, just no, that is insane. Our whole job is designing these systems, and we do not trust them even a little bit. And then they say, well, they fixed it with blockchain, and then it would appear that the engineers don't think that that's a viable solution. By the way, feel free to interrupt me at any time just by unmuting yourself on Zoom if you have questions about any of this or anything I say next. And I should be checking the Slack, but my screen is a little occupied. All right, so okay, so what really is the status of this kind of software pessimism? If you look into your terms of service of literally any piece of software you own, the top one is Adobe Acrobat. You'll see things like, we disclaim all warranties, right? In that thing you never read, there's a part about how you have many obligations, and there's a part about how they have very little obligations. In particular, you'll see that in the Adobe one, they say, we do not guarantee that our software will be available, uninterrupted, timely, secure, or error-free, which means basically that if you're doing your taxes on Adobe and it just deletes all of your files, that's kind of your problem. It's not their problem. And if you go on any Unix system, I actually use my own for that screenshot, and you do GCC -- version, there's this kind of alarming message, which is no warranty, not even for fitness for a particular purpose. All right, that means that the software that compiles all this critical C code is not guaranteed to have fitness for any particular purpose. All right, and of course Emacs as well. Basically every piece of software. All right, except maybe flight software, and I might touch for a moment at some point about why should software on planes be really different. All right, here's a couple of cases in point. The first one you may have heard of was a few years ago, 2012. I guess more than a few. Geez. Anyway, high frequency trading group, Knight Capital. They made a major update, and then they went home and had a good night's rest. And they forgot to do something mundane, which is copy new code into a given server. And the time it took the engineers to drive to work, so 45 minutes, Knight Capital basically lost $400 million by accidentally having a high frequency trading algorithm which was doing stupid trades. All right, so imagine you get into your car, you drive to work. By the time you get there, between the time you get into your car and the time you get to work, your company has lost $400 million. And maybe it's your fault because you wrote a bad line of code. This is, it's not great. Knight Capital, ended up going bankrupt the year after that, somewhat unsurprisingly. One you may have heard of is Equifax. Now, Equifax wasn't a software error in the sense that it was just negligence. They were actually hacked into, but they did exploit a publicly known issue, which means that there was negligence in some sense, which was, this Apache struts wasn't updated in a sufficiently timely manner. Hackers got in, very clever, but also they exfiltrated quite a bit of data. In particular, they got the credit info of 148 million people, which means that, if you flip a coin and it comes up heads, that's the odds that somebody out there has your, social security number. And something kind of interesting happened, which is I looked up the profits of Equifax that year, and they posted 3.3 billion in profits that year. They were fined 700 million, which seems like a huge amount of money. But from their point of view, what they did was kind of fine because they posted that huge profit despite the fine. So what I'm just trying to get at is, software bugs. There are financial issues that there's loss of life, and there are examples with software issues that cause loss of life. But this is kind of a this is a different issue, right? It's loss of money, which is just which is turns out can be quite serious as well. And then there's an ethical issue, which is Equifax. What they did from their point of view financially is relatively fine, but ethically, what happened was terrible, right? And so if we want to be ethical people, which I hope everybody here does, then we probably better think about what happened to Equifax and how that can be prevented. All right, so that's the philosophy. Now the pragmatics. Both of these were not just software issues. They were human issues. They were, lack of updates, lack of monitoring, lack of a lot of things. But, they were in part software issues. And they were definitely a mismatch between the intent of a system, including a software system, and its actual behavior. So, the testing environment versus the deployment environment for Knight Capital, and access to information, which is supposed to be only to a set of privileged people, and obviously that was not the case for Equifax. So this intent is a subtle issue that I think Phil touched on yesterday. But definitely, if we want any chance of addressing the issue in any way, you better have a formal language that allows us to express intent. All right, that's the only way you can move forward. You need a formal language, a language that's mathematically precise, because otherwise, we're just speaking at each other and like staring at code. And it has to be able to, say the things we want it to say. All right. So technology can't fix all these issues. Obviously, intent is something that's very murky. It's in the mind, of some humans. It might not even be clear in those minds. And even if it is clear, communicating that intent to a computer is both difficult and sometimes impossible, because if you say only give this information to people I trust, I mean the notion of trust is somewhat murky. But here's an example of one of the big victories of a theorem prover, which is the ComCert C compiler. All right, I showed you this absence of warranty about GCC earlier. Well, a bunch of very bright people came in. They ran a series of very clever tests designed to expose issues in C compilers. And they including ComCert, this compiler that was entirely verified using the Coq interactive theorem prover. And their conclusion was, ComCert is the only compiler with no middle end bugs. They didn't find bugs in the front end, which speaks to their diligence. But the middle end, which was the part that was verified, they found no bugs. And it was the only one. It was the only compiler in which they found no bugs. All right. So there's something to be said about the effectiveness of this approach. All right. So what is Coq? So people call it an interactive theorem prover, which it is. So as we will see in the tutorial that follows, basically the user has a language to write specification. The user has a language to write programs, which I call implementations. And then the user can express the fact that the specification corresponds to the implementation, or vice versa. And then there's an interaction phase where the user gives some information to the system, and the system tries to check that the specification matches the implementation. And this checking process, right, is very, very trustworthy, right? The part that ultimately certifies this check is a very small and very trusted part of Coq, right? So I'll talk more about that in a minute. All right. Coq is not the only interactive theorem prover. It's the one I'm familiar with, which is why I'm presenting it. If I was familiar with any of these others, I'd probably present one of those. The notable ones are Isabelle, HOL, which stands for higher order logic, PVS, which I guess is mostly used at NASA these days, and Lean, which is gaining a lot of popularity these days. All right. So what are the strengths? Why should you use Coq instead of Z3? Well, it's extremely expressive. And to demonstrate that, you don't actually have to read this whole thing, but I will say that this is the fundamental theorem of algebra, which says that every polynomial has at least one root in the complex numbers. And you cannot express this in Z3. It doesn't make sense to talk about every polynomial, to talk about, there's some root in the complex numbers. And not only can you express this in Coq, but you can prove it. I actually grabbed this from a library somewhere where they had proven this fundamental theorem of algebra. All right, so you have all of mathematics at your disposal. The other thing is that like I said, the checker that actually certifies the proofs that are built by interaction with a human is less than 5,000 lines of code. All right, which is not nothing, but it's not the 500,000 lines of code that Z3 relies on. Right, and Z3 has no such thing as a kernel. Right, everything in Z3 is doing the proving, whereas in Coq there's a big layer that's like the human interaction layer that does a lot of massaging, but the thing that actually checks the proof, the kernel, is distinct and it's well isolated. One thing that's nice, so Z3 is nice because you can ask it to prove something and it can say yes, and you don't need to give any additional information. But it can either run forever and not terminate, or it can say unknown. I just don't know how to prove this. I don't know how to refute it. I have no idea what's going on. In Coq, that's never the case. All right. Sometimes things are slow, but you can always unpack the proof. As a human, you can always give enough information for the proof to ultimately occur. All right. That being said, there are some weaknesses. It is significantly harder to use than Z3. It's not a push button solution. It requires a certain amount of what I call proof engineering, which is like software engineering. You need to organize your proof. You need to understand what your lemmas are. You need to understand how the system likes to consider things. And hopefully we'll touch a little bit on that later. And my third point is it is significantly harder to use than Z3. It really is. But the payoff, right, really the ultimate, final thing you get is potentially huge, right? ComCert, you can't do ComCert with Z3, really. Z3 is for proving small, very determinate, relatively simple properties automatically. And those properties might be large in terms of lines, but the conceptual properties need to be simple. Whereas ComCert is a compiler, right? It compiles C. It's complicated. It's got lots of layers, and it requires a lot of knowledge. All right. Notable accomplishments. I've been talking about ComCert, so I won't really say anything more about that, except that it is ISO compliant, which in itself was a challenge because they needed to take ISO C, understand the English language specification, and then turn that into the mathematically precise specification. And same for the underlying architecture. And then they needed to express what it meant for a compiler to be correct, though this is kind of a well-known field. The odd order theorem, which is kind of the most impressive pure mathematical achievement in Coq, which is, a group is a mathematical structure. Being a simple group is, a desirable property of this mathematical structure. It's related to being solvable, which is related to, this famous theorem that says there's no formula for polynomials greater than 5 for expressing the solutions with radicals. And basically, this mathematical theorem is, one of the big stepping stones of a big classification theorem, which just says, finite simple groups of odd order are, this particular class called cyclic. The paper proof takes hundreds of pages. All right, so the paper proof is so big that it's actually very hard to just read it all, even if you're an expert. And they managed to formalize that entirely in this system. And so now it's basically one of the most trustworthy theorems out there. JSCert, I just mentioned a couple others. JSCert is a fully formalized JavaScript semantics, which surprises me a little bit because that sounds hard to do. And basically an evaluator for those semantics, which is proven correct, which is kind of a reference implementation for JavaScript. Verdi is a language for proofs about distributed systems, which I think is very interesting. Not necessarily software systems, right? Though most likely they are software systems. But Verdi can express things about distributed systems and the way we build consensus. So like how, a server will eventually, have consistent data with other servers, things like that. And these algorithms are subtle and they're important. And so it's nice to have a way to express these things. And it's nice to know that people are working on these verifications. Coq R is a formalized R semantics, if you're familiar with R, which again, I think is crazy because R is a very subtle and complicated language. So having the semantics of a language formalized in Coq is kind of an impressive thing. Gopal asked me to include a few theorem statements in here, which I'm happy to do. I don't expect you to understand any of these, but it's nice to see that the specification is compact, right? The proofs are complicated, but the specifications are compact. And it's kind of this mismatch between the size of the specification and the size of the implementation of the actual compiler, which is really the benefit, right? You expect the specification to be simple, but the implementation to be complex. And here, yeah, all it's saying is, if my C program is, is somehow a correct C program, which is say doesn't have undefined behavior, then, if my compiler succeeded, then the assembler semantics, which is that part on the right, is, somehow equivalent in what's called a backward simulation to the C semantics of the original program. For the all order theorem, I'm not going to go into this one. It's a technical question about group theory. It is kind of nice to see that this tiny little theorem is the thing that takes 300 pages to prove on paper. And a similar theorem to the CompCert one, but for JSCert. And Verdi, yeah, something about eventual consistency. So because Verdi is about concurrent systems, it's nice to know that, if you've proven this property called weak fairness, something is always going to hold eventually. And what's going to hold eventually is that if a client asks to get a resource, eventually they'll get that resource, which is actually, a subtle property. And Coq, I'm sorry, the formatting got botched a little bit. It's a theorem like CompCert. They didn't take the time to express it as cleanly as CompCert did. All right, bunch of other notable projects. Not all of those are in Coq, so I didn't talk about them as extensively. Everparse is kind of this nice fast no copy parser. You want parsers. They are often kind of a source of incoming vulnerabilities, but they also have to be fast. So people will often write them in C. And so it makes a lot of sense to try and verify these things. Hackle, I forget what language that is. I think that's in Coq, and it's formally verified elliptic curve cryptography, which is actually pretty cool because there's interesting mathematics happening, and then there's non-trivial hacks to make this fast. It's very important cryptography be fast in certain cases, especially say if you're on a credit card. And for elliptic curve cryptography, there's a whole bunch of hacks to do that. But if anything is wrong, then your cryptography is wrong, SCL4, again, very impressive effort. This one is in Isabelle. It's a formally verified microkernel, which I think is, I said operating system. I should have said microkernel, which I think is really a tiny part of an operating system. But still, any verified, kernel is a monumental achievement. And the security properties they guarantee are typically separation, which is to say, if you have one process running and another process running, the other process can't, do anything to the first. And, now that everything is on the cloud, this is kind of something you really want, right? You want to know if you have one application running, it can't do bad things to your other very important, very trustworthy application. Certicos is a similar effort. I don't actually
know any practical, sorry, just real quick, do you know any practical uses of the cell4?
Off the top of my head, I do not, but I do know that they exist in the sense that there are clients to cell4.
Yeah, so
I think if you head over to the
is
page,
it's actually used a lot in the DARPA project. So like automated vehicles, like tanks and helicopters and stuff like this, unmanned drones, lots of different stuff in robotics, and where there are requirements for strong isolation of the processes from each other and from actually other external interference, used in production, so in supply lines, lots of stuff. So yeah, there is some stuff in chat, and they had actually a full conference recently, about 3 months ago, and lots of practical uses for cell4.
I think the time is ready.
Touch on a lot of this.
Right, the time is ready for these kinds of high assurance operating systems. I think people are really begging for that. All right, and then I just mentioned Rosscock because I wanted to mention robots because I love robots, but I don't actually know that much about Rosscock. It is a framework for reasoning about robotics programs, which is to say there are movements, what movements are never going to happen, which is something you often want to know about robots, and certain properties about how they're going to interact with the world. All right. That's all I got for the presentation. I will stop sharing. Let's see. I will look to see if there are any pressing questions on the Slack. Doesn't look like it. All right. So let's move to the fun part of this tutorial. I will start sharing again my my browser. Okay. Can you all see my browser? I'll take that as a yes.
Yeah, we can see it.
Great. All right. So basically, this Coq site, which you've been linked to, is where we're going to be working. Maybe you've downloaded Coq on your own system, in which case you can go ahead and start up now. All Coq environments roughly have this same layout, which is a big window on the left where you're going to write, a window here which I'm going to talk about a little bit more later, which basically contains your proof state, so the things that you need to prove as the user, and this bottom right is feedback of various sorts, typically error messages or just printouts. Great. So once you've opened this up, like I said, this is kind of annoying, so you can delete it. It does allow you to save and tweet, I guess, what you've written. But if you want to delete it, you can just right-click, inspect element here, and you get this funky thing here, where if you mouse over, you'll see it selects different regions of the screen, and those regions are just what the browser is rendering. So if you just click on this, which is the little hastebin box, and you right click and you say delete node, then the thing is gone. I haven't found any other way to delete that thing. And so now if you accidentally click on this button, which you probably don't need to do, you can click on it again and get the whole panel back. All right. That's out of the way. If you go to the other link with the tutorial.v file, you'll see that this is the file we're going to work on today. If you do raw, Control A, you can select the whole thing, and you can just paste this right into the buffer of Coq. I'll give you just 1 minute to do that, and then we'll start stepping through this. All right, I'll assume you've done it or are about to. So in Coq, you have a buffer which contains all of your code and specifications and proofs. And Coq is going to process these lines one at a time. You want the whole buffer to be able to move up and down and edit different things. But you also want Coq to process only one line at a time and basically hold its state at the line you're kind of at. So how do you move Coq? How do you have it process an additional line? The shortcut here is meta n, but you can just click on this down arrow. And you see if I hover over it, it tells you what the shortcut is. So if I click once, it's going to read this line, which is a bunch of import statements. And that actually takes a little while because Coq standard library is relatively large, and the Coq system is not incredibly fast. So it takes a couple of seconds, but only a couple of seconds. All this is running in your browser, by the way, which is kind of nice. Coq is written all in OCaml. OCaml has a backend that just generates JavaScript. And so all of this is just the whole Coq software system, compiled down to JavaScript and running in your browser. All right, so now I'm going to use the shortcuts. I'm just going to walk through this first line. All right, so Coq is a type programming language. It's a pure programming language, so it's basically the closest language to it is Haskell. It's designed to be similar in syntax to OCaml, but it has its own flavor, which I'm going to try to explain. So, all right, so you can just write the number 3 and give this top-level command, which is called check. And check just takes in any program or expression in the Coq programming language and prints its type. And in this case, I ask it to check the type of the number 3. And you see down at the right here, it says that the number 3 is of type nat. You can also ask what is the type of 3 plus 4? Well, that's also nat, which is reassuring. Type of true is bool. And the type of true and false is also bool. All right, not too surprising up to now. Of course, a programming language is kind of useless if you can't compute with it. And the command to compute an expression in Coq is a little bit elaborate, but it's eval and then compute lowercase in, and then the program itself. So if I do eval compute in 3 plus 4, it's actually going to do that computation, and it's going to come up with the number 7, which, again, is reassuring. And if you do eval compute in true and false, you get false as expected. And, true and true is true. So, right. So you can play around with this. You can try, true and 3, and you'll get an error here, which is to say, 3 is nat type, whereas you're trying to AND it with something. It sure had better have the bool type. There are no, well, all right, that's not true, so I won't say it. In general, if two things don't have compatible types, they will not play nice together, which is what you'd expect. But it's also very different from a language like Python, where Python is really going to try very hard if you give it a number to see if that number can't be turned into something that the function wants to accept. Coq does not do that, because it's trying to not have any errors. All right, so there are no print commands in the Coq programming language. All right, so if you type fail and then any command, and that command fails, then the fail command will succeed, which is a confusing way of saying if I do check print, it's just going to say there's no function called print. Yeah, so that's just saying there's no print, there's no read, there's no, launch missiles. Coq is a pure language. It can have no side effects. Okay, that being said, once I'd written this little piece of tutorial, I realized that there's a thing called print in the Coq system, which is different, and I just didn't want any confusion. So the top level print command, you can pass it in things and it will work. And basically, if you pass it in any name like bool, it will do its best to find the definition of that thing and print it out. All right, so bool is actually just defined, as you can see in the bottom right, to be a sum type with a true and a false. I'll explain what subtypes are just right next. Yeah, I just want to take a beat. If anybody's confused at this point, feel free to ask questions either to me directly or in the chat. All right. So immutability, again, very important concept in Coq. But that doesn't mean we can't write plenty of interesting programs. So the running kind of theme of this tutorial is going to involve this weekday type, which is a sum type, which just enumerates days of the week. Generally, pretty boring concept, except the syntax, which is probably new, and the fact that in C, enumerated types are just secretly ints, so you can use them anywhere as if they were ints. In Coq, that's not the case. The sum type is just the sum type. It only contains these 7 days, and it definitely, cannot be used as an arithmetic type by default. All right, and now we can check this newly defined Thursday constructor, and Thursday is indeed a weekday. So again, that's somewhat reassuring. All right, and now that we've defined types, we can define functions. So the syntax for that is definition. So you can take in a natural number. A little bit confusingly, Coq is going to replace the 3 letters NAT by this funny looking N, but they're the same thing, right? So if I type nat here, you see it immediately replaces it with the black bold N. And so add1 is just a function that takes an X and that adds 1 to it. And you can see that the definition is accepted, so it's a good definition. And return Monday is a function that takes in any weekday and just returns Monday. So it throws the weekday in the garbage and it returns Monday. And if we check add1, we see that in the bottom right, they don't do the replacement in the messages for some reason. So we see that add1 has type nat arrow nat, which is to say it takes in a nat and it returns a nat. Now, for those that are familiar with functional programming, you can write higher order functions, you can return functions, you can take functions as arguments, and that's all just fine. In this case, it's a very simple function that just takes in a nat and returns a nat. And return Monday is a similarly simple function, which takes in a weekday, returns another weekday, or the same weekday. All right. One thing I didn't do is test the function add1. So eval compute in, add 1 of 3 should be 4, and yes, indeed it is 4. Okay, now here's something that if you work in OCaml is going to be trivial, but if you work in languages like Python or Java, is going to be a little bit less comfortable. That's definitions by cases, right? Often you want to define a function, and often that function is over a sum type, and you just want to list all the possible cases. Now, switching in C is, of course, a thing. But again, switches in C is just really nested if-then-else's, whereas the primitive thing in Coq is this case statement. So here we want to define a function which returns a Boolean, and basically we just want it to return true if the input weekday is Monday and false otherwise for any other weekday. So how do we do that? Well, we use this match statement, which basically takes in the weekday and just gives you all the possible values of that weekday in these things called the branches. All right. So in the branch where we know that W is Monday, which is what this syntax means, right? We say match W with, and then on the left here, we're going to say, well, what does W look like? If it looks like a Monday, then we return true. And this is just equals and then greater than, which again, kind of gets turned into this fancy syntax. And then this underscore means anything else. Okay, So what we could have written is, Monday, true, Tuesday, false, Wednesday, etc. But that's kind of tedious. And this comes up all the time in, functional programming, that you want to do a case. You have a whole bunch of different cases, but all of them, or almost all of them, are the same thing. And so there's a special notation for that, which is the wildcard pattern, which is anything but what came before it. All right. Whoopsie daisy. All right. So this is a function that matches on the weekday. If it's Monday, it returns true. Otherwise, it returns false. This has the type we expect, which is weekday arrow bool. And if we eval compute, it's indeed false if we pass it in Tuesday. And hopefully, if we pass it in Monday, then it's true. Great. All right, so one thing you can do if you're not on the online version, but for some reason the online version doesn't work, is that you can take anything, really, any expression, but usually you'll want to put in a type, and you can say search, and then in parentheses that thing, and it will list a bunch of functions that it thinks you should see at that point. So if I do search bool, it will tell me a bunch of functions of that type. In particular, I use it to search for, like, how do you express negation? OK, so we defined a type of weekdays. Now we're going to define one last type and then, get on with it. And the type we're going to define is the type of lists of weekdays. So that's what's called a recursive type. So this is where we're going to depart a little bit from enums and C. And actually have something more subtle. So how do we define this? We use the same syntax, the same inductive syntax, but now instead of just listing a bunch of weekdays, we're going to list all the ways you can build a list. All right. So how can you build a list? You can either build the nil list, which is a list with no elements, or you can build what's called a const list, which is a list that has a weekday at its head, and then a tail, which is a weekday list. All right, and that thing returns a weekday list. Great. So now we can define a list, which is the list that contains just Monday and Tuesday, and that we build by consing Tuesday onto the empty list, nil, and then consing Monday on top of that. OK. Final kind of definition, and then you guys actually need to do something. We're going to define just head, the head function, all right, which takes a list and returns the frontmost element. So again, we do this by pattern matching, and basically, the only problem here really is that we don't really know what to return for an empty list, right? What's the head of an empty list? In a lot of languages, that would return an error or some kind of weird null value, right? In Coq, there's no such thing as a default value, as a null value. And there's no such thing as a runtime error. OK, so you really need something to put there. So what I did is I added an extra argument here, which is what do you return if it's empty? I could have used what's called an option type to basically allow returning a special value in the case that we had an empty list. But I decided to use a default value here. And now what I do is I pattern match on the list, right? So I do cases on the list. In the nil case, I return the default value. And in the const case, you see now this W represents whatever was used to build the list in the first place. All right, so W is a variable, and it represents, what was const onto the list at the time it was built. And so that's exactly the thing I want, so I just return it. And then the tail of the list, I don't actually need to know what it is, so I just put an underscore there because, you know, it doesn't matter what it is. In the same way that earlier it didn't matter what other day of the week it was. In this case, it doesn't matter what the tail of the list is. Great. And so now, go ahead.
So the syntax here for the definition of cons looks like, you know, you could treat this as a function of two arguments, or you could partially apply just the first argument. So does Coq have the notion of partial application? Can you do that? Can you do anything useful with that in this example, or was that going to come up later? Something like that.
So Coq does have partial application, including of constructors. So if you check const Monday, you'll see that this actually does type check, and it type checks as the thing that expects the rest of the list, right, the tail, and then returns a list. So partial application of constructors is perfectly normal and, you know, is often used. Are there any clever uses right here of partial application? No. When you pattern match on a list, it has to be completely applied, right? You can't, L is of type list, right? And so I can't pattern match on L and get const applied to only one thing. So that's of the wrong type. So you'll see that if I do this here, oh, come on. Sorry, I keep pressing Control N, which is definitely not what you want to press. So you see here, the error is kind of descriptive. It says const expects two arguments. But what it's really saying is that const applied to just one argument is not a list. Does that answer your question? I don't know if we have clever uses of partial application of constructors.
Okay, I just noticed the syntax looked that way. I thought there might be something interesting to do here, but maybe that'll show up later on. Thank you.
All right. Okay, so const Monday is a thing. Const Monday nil is a thing, and that is a weekday list. And so we might want to just check that head works. All right, so that doesn't do much, right? Because I've underapplied it, right? I forgot to give the default case. So that just says, okay, well, if I compute that, I get a function, right? That's what that fun underscore says. But that's it. It's a function. And if I pass in a default, which say is Thursday, then that's going to compute. But it's going to compute to Monday because that's the head of the list. And if I had, you know, something else here, const nil, paren, that's still Monday because Monday is still the head of the list. And if I just had the empty list, well, it's going to hit my default case. And so it's going to return Thursday because that's what I passed in as the default case. Great. So it would be nice to raise an error there. Like I said, you know, you have to be pure in Coq, because if you're not, and I'm not sure I'm going to explain this further, but if you're not pure, then you cannot build a consistent reasoning system about Coq programs. All right, so it's very important to be pure. All right, first exercise, define tail. All right, so take in a list and return the tail of that list. And I'll let you decide for yourselves what to do if there is no tail. So, all right, let me start my timer and just give you a couple minutes to define the tail of the list, kind of understand what the syntax is, see if you get any unexpected errors. And like yesterday, you can, you know, do the little ta-da emoticon once you're done, and then I'll ask for people to like post their solutions. as a side note, I think some people here are already very familiar with the system, so don't be too intimidated if people solve these exercises very quickly. I can't seem to get the chat to show up. I feel like I'm doing something wrong. Oh, there it is. Yes, the Zoom chat. No, I found it now. All right. Glad to see other people are answering the questions I haven't gotten to in the chat. I apologize for that. All right. So let's do this. Does anyone want to post their solutions in the chat? Great. Okay. So Thales gives a very reasonable definition, which is the following. We're defining the tail of a list. So the best thing you can do here is match on the list. And then if you have an empty list, it feels like the tail should just be the empty list again. That seems like a reasonable thing to say is the tail of the empty list. And now if you have a const W and something I want to call L prime, sorry, then the tail of the list really, because W is the head, L prime is the tail. So there you want to return L prime. And then pattern matches are ended with end. And we can see that this definition goes through. And we can also see I didn't use the W, so I could just use an underscore here. But it doesn't really matter that much. OK, were there any other solutions than that one? Or did anybody run into errors? And we can try and understand what that error means. All right, I'll take that as a no. All right, so one reason I think maybe I'll underemphasize the Lisp notation, the partial application of const, is that we don't actually really like that notation for lists. I much prefer the OCaml notation, though the Haskell one is fine as well. And Coq's notation system is shockingly powerful. Normally, list notation is just built into the language, right? In Python, right, a list is a list, and it's got that funny square bracket, and that's what you say to mean list or a number of other things. And in Coq, you can just define this yourself. And so actually the built-in stuff of Coq is extremely minimalistic because all of the additional, things you would normally find as built-ins can be defined and are all defined in the standard library. There's actually a list in the standard library, but I wanted to explain all this again. So I just want to say that open square bracket, close square bracket is nil. So I just write this notation and then something that looks like a string. And then the head, the list with only one element typically won't have semicolons, and so that's actually kind of a special case. So if I only have a single element, I'll write it square bracket, that element, close square bracket. And then if I have any number more than 2, there's this special notation in the notation command, which allows you to use these these ellipses dots, only 2, but it's an ellipsis, which really you basically write down what you would intuitively say in a comment, which is W1 semicolon W2 dot 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 WN is this thing, right? It's const W1 const W2 dot 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 const WN nil, and Coq accepts that. I stole this from the standard library. So word of warning, this notation is a little bit hard to use, but it is very powerful, and it does what you expect, which is now if I do Monday, Tuesday, Wednesday, Thursday, Friday, which I call the work week, this works, right? And then I can do eval compute tail in tail work week. And sure enough, it's the whole week except Monday. All right. Here's another function. I thought we were done, but we're not done. But I'm just going to blaze through these. So we can define a function that takes in 2 weekdays, which is, the notation is like this, and it returns a Boolean. And I call that EQ weekday. So, you should be able to guess what that does. So what you can do is pattern match on these pairs like this, which is written in the normal pair notation. And then you can just say, well, if it's Monday, Monday, Tuesday, Tuesday, Wednesday, Wednesday, Thursday, Thursday, etc., then always return true, and otherwise return false. And this is really what you mean when you say 2 weekdays are equal, right? You want to say that when you pattern match them, you get the same case. All right, so this works. It takes a little second, which is actually because it's enumerating all possible 49 cases here in that underscore, which is a little unfortunate. And here's a length function, which is a little bit more interesting, which basically just takes in a weekday and returns 0 if it's a nil. And you can see I can use my funny notation now. And if it's not a nil, if it's a const, you just kind of want the length of the tail plus 1. All right, but as you can see, the length of the tail, invokes the function I'm trying to define itself. And Coq just uses a different notation for a definition that invokes itself. And the keyword it uses for those definitions is fixed point, which I think is a terrible keyword, but that's the way it is. If you want to write a definition that invokes itself as recursive, then you need to use fixed point. All right, and if you do eval compute in the length of the work week, you indeed get 5, and if you do length of tail of work week, I would expect that to be 4, and yes, that's what we get. All right. At this point, it's 10 o'clock. Let me go a little bit further, and then once I get to the end of this, we'll take a break. Does that sound all right, Gopal? Or you think people?
Yeah, I wanted to just ask. I feel like this is just a very different topic than yesterday, and we're getting kind of warmed up. If people would be up for it, I'm wondering if we should maybe consider going a little bit longer before taking a break. Maybe going until 10:15 or 10:30 and taking a slightly shorter 15-minute break. Otherwise, we can keep to the schedule. What do people think? Do you guys want to post in chat if that sounds okay? All right, I think we have a lot of yays. Cody, why don't you pace it and see what a natural stopping point would be, maybe in like 20-ish minutes, 20, 30-ish minutes. Yeah.
All right. Let's, I'm sorry to say that I'm not actually sure exactly where we're getting 20 minutes, but hopefully we'll get past the first exercise.
Okay.
All right.
Good. Let's keep going.
Great. All right. So now that we have equality of weekdays, a pretty natural thing to do is define membership in a list. And this is, again, a fixed point, right? And it's kind of like length in the sense that you want to go through the list recursively, calling yourself, and just basically, or all the equalities against a given element. All right, so I define as a member, I want to say, I want to define a function which, if W is a member of L, then it returns true, and otherwise it returns false. And like I said, the theme of this tutorial involves this function, basically showing that it actually does what you expect it to do. And but the definition is relatively simple, right? We just say if L is the empty list, then W is definitely not a member of that list, so you can return false. And if it's not an empty list, right, if it has a weekday at the head of a tail, then I'm going to check whether W and W prime are equal using my equal weekday function. And then I'm just going to OR that with the rest of the list. Okay, so there are different definitions, and I would encourage you to play around with the different definitions. There's an if-then-else construct in Coq's programming language, which you can use. But this will serve us well. And if you ask if Monday is a member of a work week, you get true. And if you ask if Sunday is a member of a work week, then you get false, which is kind of the expected behavior. My normal programming process is if 2 tests pass, that means the function works. But that is sometimes wrong, which is why, I am involved in this kind of theorem proving shenanigans. Okay, so we're done with the programming language. All right, this was a tiny, very compact course on functional programming in Coq. We're done with that. Now we're going to take all these functions and we're going to try and prove things about them. So we're going to try and build specifications and then proofs of those specifications. All right. So one of the simplest specifications, certainly one of the most common one, is equality. All right. So one thing that's a little confusing in Coq is because equality as a predicate is so common that the normal equal sign is reserved for the predicate equality. All right. So what you would write equal in C is not this. This is more akin to what you would write as equal equal. All right. It's also not quite the same, but it's much closer. All right. So Monday equals Monday is a specification. All right. It's a predicate. And so I can just write Monday equals Monday, and then I can ask, well, what's the type of that? And Coq tells me, oh, this is of type prop. And prop is the type of specifications. All right. It's not bool, because propositions can be arbitrarily complex things where we don't know whether they're true or not. And finding out involves significant amount of effort and proof process. Right? Whereas bool is just a thing that either evaluates to true or evaluates to false. Prop is the type of specifications. It doesn't actually have a definition in Coq. It's one of the rare built-in things. And, you know, Monday equals Monday is of that type. Great. Okay, so now we can express a bunch of other specifications. And the first one we do here is what's called a for all statement, a universal statement, which just says every weekday is equal to Monday. All right. Now, this might seem confusing because it's not true, but you can express a lot of not true things in Coq. In particular, it's very important to be able to express anything you want to be true and then find out later whether it's true or not. So the syntax for this is for all. Again, Coq likes to replace some words with some symbols because it thinks it's neat. I'm not super thrilled about that feature, but anyway, for all typed in all words as one word turns into that upside down A, which means that every W is equal to Monday. All right, that's also a prop. And then exists turns into that backwards E. And exists W such that W equals Monday is also a proposition. And that one happens to be true. All right. Here's a list. All right. The basic propositions you can express are either true, which is, you know, the definitely always provable proposition. False, which is the never true proposition. And then a bunch of logical connectives, all right, which is or, and, implies, which happens to look like the function type. Negation, which is just the tilde, which should be on the top left of your keyboard if you're using an American keyboard like I am. And then the for all and exists, I said earlier, and the equality. Again, I'm noting that equality is a predicate, right? It's a specification, and it's not an assignment or a definition. If you want to assign something to something else, usually the equality you use is colon equals, right? Which is what I did in all these definitions up here. So A equals B is really the predicate, which is provable if A is actually the same thing as B. Great. Now, here's a more complicated predicate. And in particular, it's a predicate about, you know, an infinite type, which is to say, you shouldn't expect these predicates to be decidable, right? You shouldn't expect it to be very easy to check that all these things are true, all right? It would be very easy for me to express extremely complicated predicates like Fermat's last theorem in just a few lines. And these would be perfectly valid predicates. So this one just says that if L is a weekday list, then either, right, this is the or connective, L is equal to the empty list, or there exists a W and an L prime such that L is equal to const WL prime. All right. This one you also expect to be true, right? You expect lists to be either the empty list or a non-empty list with a W and an L prime in a const construct. All right. That being said, you know, it might not be true. I don't know. Great. So let me check the chat. Are there any questions about specifications at this point? All right, so I see a big question. Is it possible to short circuit the is a member calculation? And then you expect the or to be short circuiting. It definitely is not. Yeah, so it's possible to define a short circuit is a member function using the if then else. And if then else, I think, does short circuit. I don't think the Boolean or short circuits, but I don't know. Don't take me to court on that. Okay. All right. So here is our first test lemma. All right. So how do we express specifications? Well, we either call them lemmas or we call them theorems, basically. And I'm just going to walk through this one to explain how this happens. And this is where, you know, the magic happens. All right. So my lemma is for any 2 weekdays, X and Y. I should probably have called them W1 and W2, but I don't know. I don't like W1, W2, W3. It gets tedious. So I call them X and Y. And what does the specification say? It just says if X is equal to Y, all right, so I'm assuming they're equal, then X is equal to Y. All right, so this pretty clearly should be a true statement. All right, it should be provable. And indeed it is. And the proof should be easy. All right, so what I did in all this file is I wrote abort at the end of the proof. So at any point in a proof, if you decide that whatever, you can't finish it for any reason, if you're too lazy or it's too hard or it turns out to be false, you can abort. And once you've aborted, you can't refer to test 1. If I check test 1, it didn't find it. All right. So how do I prove this? Basically, I just look at the shape of what I'm trying to prove. And I'm going to apply things called tactics to change my proof obligation. All right. So what currently is in this upper right-hand side, this thing, is my current proof obligation. All right. So it says, if you want to prove your original lemma, here's what remains to be proven. All right. And what remains to be proven is everything, because I haven't done anything yet. All right. So what appears here is this one goal, and it's the whole thing that I wrote down as my lemma. All right. So I know for a fact that if I have a for all x, y, something implies something else, I want to start with a bunch of assumptions, right? Take an arbitrary x, take an arbitrary y, and assume that x equals y. So I can introduce all these assumptions by using the keyword intros. All right, and let me just take a beat to say whatever is between the word proof and either the word abort or the word QED that I'm going to explain later, which you can use when you're done with a proof. All of these things are tactics, all right? And tactics are the language in which you can resolve proof obligations in Coq, all right? So in Coq, you can use tactics to change proofs. And tactics always start with a lower case letter, all right? So that's how you know something is a tactic, essentially. All right, intros introduces my hypothesis. And so as I run this, it's going to change my goal into a different goal. All right, now I have a different goal in which I have things above this line, which are my assumptions, and things below this line, which are my remaining proof obligations or goals. All right, so what do I have as assumptions? I have assumptions that x and y are arbitrary weekdays. And I have an assumption called H, and Coq chose that name for me. I can give it a name to choose if I want to, but I decided to let it choose for me. And the assumption H is the assumption that x equals y. All right, well, that's encouraging, because if I assume that if I have it as an assumption that x equals y, I should really be able to deduce or conclude that x equals y. So how do I do that? I use a tactic called apply. All right, apply takes an assumption and it tries to apply it to my conclusion. In the case where the assumption and the conclusion are identical, it's going to succeed. And so here I get a success. It successfully applied, and so it resolved the goal. All right, it removed that one goal from the system. If I had other goals, I would now move on to having to prove those goals. But I don't have any more goals, so it says no more goals. And this, if you're used to Coq, is a very happy feeling. No more goals, you really feel pumped. When you have no more goals, you can do QED instead of a board. And that will succeed. And now test one exists, all right? Because I've proven it and I've managed to discharge all my goals, I can do QED, and now test one will live in my environment, all right? And if I do check test one, it says, here it is. And in particular, I can use it in different theorems I'm trying to prove as a lemma. All right, it's 10:12. I just want to show that QED does in fact check that I'm done. All right, so if I'm not done, if my goal is still unfinished, QED is going to complain. It's going to tell me you thought you could type QED because you were done, but you're not done. All right. So basically, I've gotten through the main content of what I wanted to tell you guys. The next thing I wanted to say is just this table is a cheat sheet, right? It's kind of a magical thing where you look at your goal, you look at what it looks like, and if your goal looks like, you know, one of these, then I can tell you what tactic to apply. All right, so there's a bunch of tactics that I list here in this first column that basically says if you look at your goal and it looks like this, here's a tactic you should probably apply. I'm not guaranteeing that you should apply that tactic, but I'm saying you're probably in a good shape if you use that tactic. Now, if your goal doesn't seem to be making much progress, or if it's not of one of the forms here, or if the tactic doesn't work, if it gives you an error, then usually that means that you need to use something in your hypothesis. All right, and using something in your hypothesis, you know, comes from this column, right? So you look at your hypothesis and you look at the shape of the hypothesis, and depending on the shape, you use the tactic that's in this column. All right, so we can go back up here and we can see that there's no magic at this point, right? When I wrote proof, I just looked at my goal. I saw it started with a for all and then an implies. And I see that in my little column, if my goal has a for all, I can do intros. And if it has an implies, I can do intros. So there, at that point, I did intros. All right. And now I have an equals. And my cheat sheet says that if I have an equals in my goal, I can try reflexivity. And that fails. All right. It fails because X and Y are different things. They're not the same thing. Okay, so that fails. So I'm stuck with my goal. So now I somehow need to use my hypotheses. My cheat sheet says that in my hypotheses, if I have an equals in my hypotheses, I can use rewrite or inversion. But also something that I don't say here is that if I have exactly the conclusion in my hypothesis, I can use apply. All right. So that's what I did. But I could have used the other thing, which was reflexivity. I'm sorry, which was rewrite. And that does work according to the cheat sheet. And then what I get here is y equals y. And y are the same thing, of course. And so there, reflexivity will actually work. All right. So proof by cheat sheet. All right. I am going to call the break now, actually, because my throat is getting a little sore and I've gotten through what I wanted to get through. And so I'll meet you on Gather. And when we come back, we can start working through all these problem sets. And basically, it'll just be you guys try something on your side, and then we come back and I'll give the solution. How does that sound? Gopal, you think that's good?
Sounds good to me. While why don't we reconvene at 10:30? Is that okay? It's a slightly shorter break, but I think that'll just give us more time to get through things.
Great. Yeah, so for the people that weren't in the conversation we had on Gather, this short-circuiting behavior, yeah, somehow it's not, it barely makes sense, right? Coq, yeah, I wrote eval and then compute, and there are other things to compute, and the different things sometimes have different strategies about how they're going to evaluate things. I don't actually know if it's possible to make those strategies, evaluate the left-hand side of a branch first and then not even do the right-hand side of a branch. I don't actually know if that's the case. And this is kind of a problem. I think pattern matching in Coq tends to be eager, and so short-circuiting isn't really a thing. So, all right, I'm going to let somebody else handle that destruct question. All right, so let's move over to this trivial equality. Did anybody run into difficulties where they tried something and it didn't work? I'm going to take that as a no, so I'm just going to work through the proof. So Monday equals Monday is reflexivity. Whenever you have the same thing on the left and the right, then you're in good shape. Great. And it really is nice to know that the proving software is doing something. In particular, reflexivity doesn't work if you have different things on different sides. So I'm going to abort this proof and not finish it. All right. Here's something that's much more interesting than proving Monday equals Monday or x equals y implies x equals y. And that is prove something about computation, right? That's the whole point of the system. All right, so I have my old function return Monday. And at any point, I can do print return Monday or print the name of a thing, and it'll remind me what the definition was. And the definition here is a function that takes in an argument, which is underscored here, throws it in the garbage, and returns Monday. Great. So, okay, so I have return Monday on the left, applied to Friday, equals Monday. So those, strictly speaking, aren't the same thing. But I can call compute here, which is actually a tactic, as well as a thing I can give to eval. And compute will compute, right, on both sides. So if I compute here, you see, before I have return Monday, Friday, and if I say compute, then it's going to evaluate that thing, give me its result, and that result is Monday. And so I can finish here with reflexivity. And there I'm done. No more goals. I can do QED. All right. Why doesn't everybody do the next one, which shouldn't be excessively hard? Feel free to ta-da in the chat. All right. Did anybody run into an error when they were trying to prove this? Should I be in some confirmation? Well, no. Usually in the not online version, you'll see, a message that just says, test 3 is defined. I don't think you see that message here. So yeah, so it's a little bit, yeah. So if it's not complaining, then it's happy. Though the return code 0 comment is worrying me a little bit. I assume you mean.
Sorry, I just meant like in Unix, if it's return code 0, the shell doesn't tell you anything, everything's good going.
Yes, this is definitely the Unix philosophy of if you're not complaining, then everything's good. All right. Generally, if you see no more goals in your buffer, then you're done. There are some extremely rare cases where you can see no more goals and then QED will fail, but those are so rare as to be not really worth mentioning. All right, so here, I mean, it's the same thing. Computes the length of the work week, turns out to be 5, and you can do reflexivity, and that'll work. Not used to this tabbing. All right. All right, but that's all well and good, but all this is not really buying us that much over normal testing. So what we really want is to talk about behavior that's over, all possible inputs, right? So, I mean, we know that return Monday is always going to return a Monday, and we want to express that fact and prove it. Great. So let's give a shot at this one. I haven't really explained how it will work, but why don't people try it and see if they can't get it? Yeah, my console stops printing messages for some reason. I don't actually know how to fix that, but here in the top right-hand side, you can do reset worker, which I think will reset the worker, which is to say it'll start over the Coq process entirely. And then, you can, if that works, then you should be good to go. You can go back down to where you were previously. All right. Okay. Talis, you want to give us your proof? Yeah, dang it. I'm sorry, Dennis. Not sure what's wrong. You might want to try changing your browser, opening it in a different browser. All right, so what proof do we have? Okay, so we have intros reflexivity, which definitely works. And we have the proof I intended, which is intros compute and reflexivity. And then we have the other form, which is intro reflexivity. Intro is, it will only do one introduction, which is sometimes useful, and it will also fail if there are no such introductions. So it does one and exactly one. Right, so Coq just, I honestly do not know, but there are a couple tactics that are just special keywords, and reflexivity is one of those. And then other tactics that are like defined in terms of other tactics, so they're not really built-ins. Oh, no, I'm sorry, I take that back. The ones that are colored red, I think, will fail if they don't solve the goal. Yes, thank you, Gregory. So yeah, so they are substantively different. Yes, they will either fail or they will succeed, and you will have one less goal. Though I think auto will either succeed and solve your goal, or it will fail, but it won't give you an error message, which is kind of the odd duck out. But let's not talk about auto right now. All right, so next proof. Okay, so if we do intros and compute, we get this horrible thing, which is all the cases, right? It's not horrible, but it is not great. And it's certainly not, we're not done here, right? I can't do reflexivity here. And the error message is horrible, but it's just basically saying these things aren't equal. All right, so what is going on here? What's going on is that I really need to consider what the weekday is, right? Because if I print EQ weekday, you see that this is defined by pattern matching on the arguments, right? And so if I don't know what the argument are, if it's just this abstract X, then it doesn't know really what EQWD will compute to, all right? So in this case, I absolutely need to do something with X. And the something I need to do with X is look at all the possible cases. So if I do case X, now instead of having one goal, I have 7 goals. And that is kind of an important thing. It's important because this is always the case when you do a case, which is it looks at all the possible things that X can be. And if X is defined as an inductive, which it must be if you're calling case, it will create as many goals as there are possible inductive constructors for X. All right. So reasoning by cases, this is what you do, right? If you have 5 cases, you reason by cases. Now you have 5 things you need to consider. All right. Now I'm going to use a special keyword called dash. And what dash does is if I have 7 goals, it will focus on the first one, which in this case is equal WD money equals true. And it won't allow me to focus on the next goal until the first one is done. All right, so I basically need to finish this first goal, and then I can focus on the next one. Right, and so here I can do compute, and I can do reflexivity. That works, and it tells me you're done, but there are other goals. And here's what you need to do to focus these other goals. You use a dash. All right, so now I do my dash. I have Tuesday. I can do compute, reflexivity. And then I can do this basically 6 more times. So it's very tempting to just copy and paste here, you know. But if you start doing that, you're going to be copying and pasting like crazy. this is kind of an anti-pattern in programming, and it's slightly an anti-pattern in proof engineering. So I will say, that copy and pasting still happens quite a bit. All right, so let's go back up. So basically what you want to do here is a case on X, and then you want to do the same thing in all cases. All right, so there's what's called a tactical for that. So if instead of ending with a period, I end with a semicolon, then the next tactic I do here is going to be applied to all the new cases that were created. This is a very powerful notion. It's saying I'm going to create a bunch of goals, which are all a bunch of different cases, but I want to do the same thing in all those different cases. All right. So if I do case X semicolon and then compute, you'll see that instead of having, EQWD Monday equal WD Tuesday, Wednesday, it's done all the computations and all the goals. All right. And now what I want is all those goals, still, I want to do reflexivity on those. Great. And so that works. And it's exactly the same thing as if I had done this copy and paste in all those 7 cases. So this is kind of nice, right? We're already seeing a very simple case of proof automation where I do a reasoning by cases, but then I apply kind of batch tactics on all of the created cases. All right, so that's kind of nice. I'm going to let you play with connectives. Feel free to use the cheat sheet. And basically, you should yeah, I'm going to leave you 5 minutes, and you should ta-da in the chat once you're done with, sorry. Test 11, you should ta-da. No, I have not. And in fact, my tutorial, I really misestimated how long it would take to get through this. I mentioned rewrite. It's in my cheat sheet. And subst, I just not explaining. Yeah, something that is a little confusing is call a coq just likes to look nice, and so whenever you write a number at the end of a like a name, it's going to subscript the number just as it shows up. But the number is just written at the end of the, so like test 4 is, it's just test and then the number 4 at the end of that. Okay, so people are running into the something I expected, which is do something, and if that doesn't work, do something else. Which, as people are explaining in the chat, is you have to use parentheses because Coq, yeah, I don't know why French people don't know how to make bindings at the appropriate level of precedence. But if you do like, you know, reflexivity or apply H, it will try reflexivity, and if that doesn't work, it'll try apply H, and if that doesn't work, it'll do nothing. Okay, borders a little bit ahead of the curve. Please don't share the solution in the general chat so other people can try and figure it out for themselves. Thanks. One thing I'm hoping to communicate to some of you is that there's a certain game-like aspect to this where all the different tactics are your different moves. And you know, there's basically a set of a dozen tactics that are enough actually to prove almost every single goal. And those are your plays, and your adversary is, you know, is the system where, you know, it gives you a challenge, and your moves are the tactics. And there's a certain satisfaction to be had by like solving these goals. Of course, you know, some of these are, you know, relatively trivial, and in particular, you know, Z3 could handle all of these with ease because it has a lot of internal structure that knows how to solve goals like these. Okay, Jonathan is asking about rewrite. So in general, rewrite takes an argument. I'm not sure if that's what you're asking about. But we're also at the 5-minute mark, so maybe I'm going to start working through some of these. Yeah. Oh, okay. So I think Jonathan is trying to kill 2 birds with 1 stone in this test 6. All right, so all right. Yeah, so one thing that's a little bit unfortunate when you're teaching Coq is that tactics are extremely versatile. in general, you can use them in tons of different ways, and they will all support those different ways of using them and do slightly different things. And so it's a little frustrating to teach because usually somebody's going to type something and it's not going to fail, but it's going to behave strangely. So yeah, that's a little unfortunate. All right, let's go through test 6 and then we'll start knocking them out. All right, so test 6 has an and it has a bunch of for alls and implies. So I'm just going to apply the cheat sheet, do an intros here. It's going to pick a bunch of names and give me a bunch of assumptions. I have an and in the conclusion, so I can just do a split. That gives me 2 goals. If I do the first one, I have x equals y. I can just apply h here. And then the second goal is the second one, so I can just apply h0 here. Great. Did people get different solutions? There are many, many different solutions here. Some of them using tactics we haven't seen yet, but some of them, you know, like I explained in just verbally and in the chat, here, if you want to do apply h to both goals created by split, you're going to fail, right? Because the second goal, you can't apply h to it, all right? So what you might want to do here is say apply h if you can, and if you can't, apply h0. And that succeeds. All right. So this disjunction is powerful because you can say, okay, I'm going to look at all my goals, and I want to apply something to all my goals, but I want some kind of some mulligans, right? So I want to say, okay, well, apply h to all of these goals, except if it doesn't work. And if it doesn't work, then just go to the next one. And as Gregory mentioned, if you have a long list of such things, you can just do first, and then a list, and then it's separated by a single bar for reasons that elude me a little bit. That works as well. And that will just do the first one. All right, change it back to the other one. Great. All right. Yeah. Assumption will also work here, but I've chosen to keep things very, very simple. No, it's fine. There are thousands of tactics. There's just tons. And there are usually many different ways to do the same thing. Great. OK, so here's a disjunction. So usually intros is always going to be the first thing you do because you have a ton of hypotheses and you just want to move those above the dividing line here. And so yeah, sometimes you want to give names to things. So you might want to say XYZ H or XYZ little h. Some people don't like the capital letters, or XYZ my complicated hypothesis. If you're a Java enthusiast. All right, so okay. So now I have disjunction, and when you have a disjunction in the conclusion, you usually have to pick a side, right? You know, in logic, there are no sideliners. You have to pick a side. So I'm going to pick the left side here because that's what I know how to prove. That works. Now, what would have happened if I had picked my, yes, in Java, it would be camel case. Ironically, camel doesn't like camel case. All right. Yeah, thanks, Sam, for the clarification. Yeah, the double bar is not exactly the same thing as first. So if I picked right here, you know, it would succeed. It would say, okay, well, if you prove y equals z, then certainly you've proven x equals y or y equals z. But the problem here is that I'm stuck, right? I can't apply h. And there's nothing I can do. So this is one of the kind of the rare cases where you can really be stuck, right? You do right, and then there's no saving me, right? There's nothing I can do further. So the tactic succeeds, right? It doesn't fail. There's nothing I can do from here on out to solve the goal. This happens occasionally, and it's important to learn how to recognize it, but that only comes with experience. So here I do left. I get this new goal that I know how to solve, and I don't need to abort anymore. I can QED. Great. All right. Now we have a disjunction in the hypothesis. I can do intros, you know, x, y, z, h. And here I can do destruct h. And if I want to name the new hypotheses that come from destructing h, which are going to be the two halves of that and, I can do destruct h as, and then h1 and h2. And again, the notation is a little funky here, but whatever. It's the way it is. And here I can apply the correct one, which in this case is h2. Feel free to interrupt me at any time. So somebody's asking me, does this make sense as a proof? Anything that QED accepts makes sense as a proof. That's kind of the beauty of it, right? If you type something horrible, but at the end you have no more goals and QED is happy, then you don't really need to, you know, you don't need to like introspect too much. No, there is no up. Once you've lost the disjunction, you've strengthened your conclusion. You can't weaken it again. You can only go in one direction. So if you go down a branch in a proof where you strengthened your conclusion to something that you can't prove, then you're stuck. You have to go back in the buffer. You have to step back up your proof. Sorry, the question was, if I did right here instead of left, could I like undo that choice? And the fact is, there's no undoing the choice with an additional tactic. It's not possible. All right, this one is a little tougher because I have an assumption that's a disjunction, and my conclusion is also a disjunction. And so here, if I choose left, then my assumptions are too weak, right? I only know that x is y or x is z. And what I need to conclude is that x is z. But I don't know that. And if I choose right, I'm in the same case. I know that x is y or x is z, and that doesn't tell me that x is y, certainly. So when you're in that case, usually what you need to do is understand your hypothesis first. Here it's destruct h. And here you can say as h if you want, or as little h if you want to mix it up. Oh wait, it's a disjunction pattern. Yeah, so sorry, this is fancy notation, but it's useless. You can just do destruct h and let Coq pick names for you. All right. Okay, so what I've done here is when you have a disjunction in your hypothesis, you can say, okay, well, let's reason by cases on this disjunction. Either I'm in the left case, and then I can prove the conclusion, or I'm in the right case, and then I can prove the conclusion. All right? So now we're reasoning by cases, And here in the left case, I can do left, right. And, apply H. And here I can do left and apply H. Great. And because I feel like being fancy, you can do the semicolon, and then you can use this single vertical bar, which says, okay, I know how many goals I'm going to have, and it's 2. And in the first goal, you should do everything that's on the left of the bar. And in the second goal, you should do everything that's on the right of the bar, right? And I could have a third bar here and say, apply H. And then I'd get an error because it's, wait, something's wrong here. Oh, nope, I got it wrong. Yes, sorry. Here, if I had a right, apply H. All right. Here I get the error which I was expecting, which is, oh wait, you thought there would be 3 new goals, but there's only 2. All right, but here there's exactly 2, and I'm giving it exactly 2 series of tactics. And so it's going to apply the first one on the first one and the second one on the second one. Okie doke. Are there any questions at this point? I feel like I should be pausing a little bit. I will take no questions as assent. I haven't really been doing online teaching, so I don't know what the tradition is for like how much reactions to expect. All right, here is a reaction. Somebody is completely lost. So a good intro tutorial is a rare thing. I do have some links at the end. The first link is just go to coqinria.fr, and that just has like a tutorials tab where it lists a bunch of tutorials. I think, going through this tutorial again and taking a beat would probably be helpful. But then just going through the list of like, this list right here, like short tutorials and videos, can be very useful. In particular, Yves Berthaud is a great guy and a very good expositor, though the tutorial is 2006, so Coq has changed since then. And then Andrej gives one in 2011, probably also very good. And then video lectures in French, which, I guess that depends on your inclination. And then what I was recommending is the Zulip, which is here. And if you go on the Zulip and ask almost any question, somebody will be there to answer it. Right. Contradiction only applies if you have false in your hypothesis. So if you really have false in your hypothesis, you can apply contradiction. But if you have something that is, known to imply false in your hypotheses, then contradiction isn't going to help you. Right, and Software Foundations is a very good tutorial. Dennis, if you don't mind my putting you on the spot a little bit, did you have experience with any functional programming language before this tutorial?
Sorry. I did a little bit with Scala, but very little.
Okay. And do you feel like the programming part is okay, but then the proof part is complicated, or are both parts equally confusing?
No, it's just the overall syntax, how quickly we jumped from, like, the initial part was, pretty clear, but then everything afterwards with all these, intros, right, left, like, what do they even mean? It's not easy to understand.
You're right. I agree. I'm taking slightly advantage, and that's a bad thing, of the fact that a lot of people here have some prior experience. And I'm also using the cheat sheet extensively, but the cheat sheet is a little bit under-explained. So yeah, so intros is just standalone. You can always apply it, and it will introduce hypotheses. And then left and right, applies by themselves to a goal, right? So just left period or right period. And those, will apply if you have a disjunction, an or in your goal. And then some of these other tactics take in arguments, right? So apply takes in a hypothesis name, and rewrite takes in a hypothesis name. So all that is a little bit non-trivial. And then all these different tacticals, the semicolon, the square brackets, those are all, yes, there are quite a few of them, and I've been kind of fire hosing them at you. So I apologize for that. One thing that's a little bit annoying is that the very first steps and the steps after that are very different, right? You want to learn a very, very small number of tactics at first. You just want to apply, intros, left, right, and destruct. And later on, you want to learn as many tactics as you want to reduce your workload, because there's a lot of things that become repetitive. And so you really want to reduce your workload. So I will, Dennis, I'll post solutions for all of this. So you can take a beat and come back to this if you want later. And, like people were saying, Software Foundations has an extensive introduction. I think it's probably the best one out there. Actually, I should have mentioned it first. The Adam Chappell book is probably best read after Software Foundations. All right. Let's do intros again. Great. So now we have x equals Monday, we have y equals x, and we're trying to prove y equals Monday. Okay. Well, reflexivity doesn't work here. Worth a try. And so what my cheat sheet says, you can do rewrite. So we can try rewrite h. That also doesn't work, because rewrite h just tries to match the left-hand side of the equality in the goal, and x doesn't appear in the goal, so rewrite h fails. But rewrite h0 works, because it finds a y in the goal, and it replaces it with the other half of the equality, right? So, when I do a rewrite this, it basically treats this as a computation rule in some sense, right? It's going to change the goal such that everything in the goal that's this gets replaced with this. Okie doke. So now we have x equals Monday, but that's exactly a hypothesis, which we can apply, and we're good. I am a very slow typer. All right. So Berkus is saying Z3, please just try and just do as much as you can. So like I said, there isn't any way to actually call Z3 from Coq that's well supported right now. There are ways, but they're not well supported. But there are tactics that are more powerful. I did not teach them to you because the low power tactics like intros, destruct, apply are actually needed at some point. And unfortunately, if you learn the powerful tactics first, then like knowing when to use when the powerful tactics fail, they're completely uninformative. They're just like, this powerful tactic failed. And so you end up, learning the low level tactics and then learning when to apply the high level tactics. All right, so this one is actually a little finicky, right? Because if I do intros here, the conclusion is false, right? So how could I possibly prove a false conclusion? All right, the only way to prove a false conclusion is if I have a false hypothesis that entails a contradiction. And luckily in Coq, right, when you have a sum type, each variant of the sum type, so Monday and Tuesday, cannot possibly be equal. All right, that's just a fact. Just like true and false are two different things that cannot possibly be equal. Monday and Tuesday are two different things that cannot possibly be equal. Now, the actual like low-level proof of Monday equals Tuesday, entails false, is really finicky. And so you never want to actually do this one by hand. So you want to use a more high-power tactic. So the only high-powered tactic I'm introducing in this tutorial is inversion. So if I do inversion H, the inversion tactic is smart enough to know that Monday and Tuesday have to be different, and therefore any conclusion will follow from an assumption of Monday equals Tuesday. All right. Okay, so this was the teaser where I introduced some of the basic tactics. Probably should have spent a little bit more time, as Dennis mentioned, explaining the syntax of the tactics. But those are the basic tactics, and they can be used to do quite a number of things. And the real thing I'm going to do, which I called serious stuff in my tutorial, is we have these programs that we wrote, but we want to know that they're actually like good programs that do the right thing. In particular, the equal weekday program, it would sure be nice to know that, yeah, it's actually equality of weekdays. So that's our first real lemma. Oh, Gregory, you're bringing up all sorts of stuff I didn't want to talk about. That's okay. I think it's good to have too much information.
You shouldn't talk about proof terms.
Yeah, my dream is to keep that a secret for as long as possible. I think it's interesting philosophically, but I think it's very confusing to confuse the notions of of definitions and functions and of proofs, and ultimately not that helpful. All right, so Phil is explaining that there's all sorts of powerful automated tactics, which is cool. Alexander is saying Isabel Hole is even better at automated tactics, which is probably true for the time being. All those things are true. I will say that if we have time, we'll see some of the automation in Coq, and it is less impressive than the automation in Isabel, but it's also, at some point, the automation only takes you so far. And if you want to prove serious, serious business stuff, you're going to want to use automation in a very constrained manner. All right, So first real lemma, which says if x and y are equal, then EQWD x and y is going to return true. So does anybody have a solution for this? Chad Brubaker is asking how you shell out of Coq. That is an oft-asked question to which I do not have the answer. I think you have to have Coq installed on your machine, certainly. And I think there's a command line interface that allows you to export this horrible XML format of Coq's internal state. And then you can also write plugins, which are OCaml programs which have access to Coq's internal state. All right, Michael has a solution. He says we do intros and then we can do rewrite H. What does that do? That puts us in a situation that we've seen before, right? Which is the EQWD Y and then Y. And we have that proof from earlier, which is case Y and then compute and then reflexivity. All right, and again, if we didn't use semicolons here, we'd have the 7 goals.
So doesn't test 5 already encode this? Can we somehow apply the prior lemma directly?
Yes. So if I do rewrite H, and then I do check test 5, it's going to say, oh, here's what test 5 is. Okay, it says for all x, weekday xx equals true. This is weekday yy, and there's no for all. So it's not exactly test 5, but certainly it feels like a special case of test 5. And that's exactly what apply does. It figures out what special case to construct. In this case, it's, you know, applying this lemma with x as the y. And so if I do apply test 5, that will work. Comment this out. One thing I've learned the hard way is when you do a proof and your proof ends up not working, you often want to delete it. And then almost immediately later, you want to remember what it was because you're in a similar situation. So these are the deep secrets of Coq theorem proving. Yeah, Alexander is mentioning Y3, which is built on top of Coq and SMT solvers. Yes, I have some experience with Y3. It's a complicated beast, but it is very powerful. And it is, I mean, Y3 is really used with its own imperative language, and its whole purpose is to prove things about the execution of the imperative language. One thing that's nice in Coq is that you want to use Coq as, you know, a mathematical language for expressing complex things, which is not really how you would use Y3. All right, great. So we can use earlier statements just by apply. All right, and now the other direction. Okay, so this is where things get kind of serious. Okay, so we have something that is true, which is equal WD xy computes to true. And then we have x equals y. But like, if I do compute, nothing happens. If I can do compute in H, which will run compute, but inside the hypothesis. And I mean, something happens, but it's not that great. And certainly it doesn't really tell me how to move forward. So what you actually want here is to reason by cases on X. Okay, but again, here we don't really know how to progress. So we want to reason by cases on Y. Great. So now we have Monday equals Monday, and that's very easy. I can do a reflexivity. Great. Oops. Great. Okay, and that was one of my 13 goals. And now we get to Monday equals Tuesday, and what we know is that equal WD XY equals true. So something went wrong here. Can somebody tell me what went wrong?
It's making us look at all possible pairs of days, even though we don't care about them because they're excluded by this predicate.
Right. Well, in some sense. In some sense, when I did case X and case Y, I've specialized X and Y, right? I've specialized them to specific cases. But somehow the hypothesis doesn't know about this, right? It forgot that X is actually Monday and Y is actually Tuesday. So the big issue here is that case X and case Y only specializes X in the conclusion and not in the hypothesis. So one thing you can do is make sure that all of your X's and Y's that you care about actually appear in the conclusion. So what I will do here, let's see. So there's like 3 or 4 ways to do this. I'm not sure what the good way is. Phil asks if lean integrates with Z3. It does not. So what I'm going to do here is I think I'm just going to do intros X, Y. And that's actually only going to intro X and Y and not this last H. All right. And now I can do case X and I can do case Y. And you see that now this equal WD XY is an equal WD Monday Monday. All right. Now reflexivity works. It shouldn't work, but reflexivity is intros reflexivity. All right. And here, okay. Now here was the case I couldn't prove, because it was Monday equals Tuesday, which is false. And so I need a false hypothesis. Okay, but I have equal WD Monday, Tuesday equals true. So I can do compute here. I get false equals true implies Monday equals Tuesday. And there I'm in good shape, right? Because false equals true is false. And so is Monday equals Tuesday. And so false implies false, right? So now I can do intros inversion H, and bam, I'm done with that. Great. So I have tons and tons of goals left. So in fact, this is 7, right? And this is 13. But once I'm done with the first 7, I'm going to have to do a case Y again, right? And so at the end, I have 49, right? I have 49 goals because I need to do every possible combination of X and Y. All right, so what I actually want to do is case X, and then for every one of these sub-goals, case Y. And that's 49 goals, 7 times 7. And then I don't actually want to do those 49 goals because it sounds like a nightmare, okay? So what do I want to do here? Does somebody have a suggestion? Yes. Okay. So Dan is saying, oh, well, first real lemma seems relevant, right? It's the same things in a different combination. Okay. you might want to apply first lemma. Let's say I want to apply it to the first thing. Apply first real lemma. Okay, it says I couldn't solve this because first real lemma ends with something equals true, and this is not something equals true. So maybe I need to do an intros. Okay, it's still saying no. Your lemma says something equals true, and you're trying to prove Monday equals Monday. All right. So what actually is the case is that first real lemma and second real lemma are two different directions of a thing I want, right? First real lemma says if things are equal, then the computation returns true. And second real lemma is if the computation returns true, then they are equal. All right, so here's something that could have happened. I could have equal WD be the function that always returns true, okay? And if I had that, the first real lemma would still hold, right? If x and y are equal WD xy returns true, yeah, it always returns true. Now that's not the case, but if it had been the case, the first real lemma would still work as advertised. Second real lemma would not, right? So a function that always returns true isn't going to imply x equals y. Okay, so the first real lemma and the second real lemma are somehow fundamentally opposites, right? So you can't use the first one to prove the second one. All right, great question by Dan. Thanks a lot. All right. So a lot of interesting discussion about tangentially related subjects. All right, so I'm going to give kind of give away the solution. So if I do compute here on all the subcases, you see that I end up with a bunch of things that are either true equals true implies Monday equals Monday, right? Or true equals true implies Tuesday equals Tuesday, or I get false equals true implies something that seems false. All right, so those are the only two possible things. Okay, so all of my 49 cases can be handled by either intros reflexivity but not all of them, right? There's at least one case it couldn't handle. But the other cases it can handle with intros, H, inversion H. Oh, sorry. H is already used. H0, say. Oh. Crud. All right, so this worked, and it handled my 49 cases. I'm going to explain a little bit why it worked. All right, so I did case X, case Y compute. Great. Now this first one, reflexivity, handles it. The second one, intros H0, inversion H0 handles it. Okay, so first goal I get is handled by reflexivity. Second goal I get is handled by this thing. Okay, so when I have two things that handle all the goals together, I can always say, oh, well, I'm just going to say, try that one. And then if that doesn't work, try the other one. That works. But it also works here, because reflexivity fails, and that's okay. It just goes to the next one, right? So when you have this case where each case is handled by some small finite number of tactics, then you can just do a semicolon here and say, okay, try it on everything that comes out. And that's usually how you do proofs, right? You end up with tons of cases, and they're all similar. They're all slightly similar. And there's only really 2 or 3 big different things you need to do in different cases. And you just OR those all together and say, just use the first one that works. And then you do a semicolon, and you just wait a couple seconds, and you just write this one-liner. Does this all make sense? Yes. There's a tactic that is like case that introduces an equality. And that tactic is called case EQ. You see, there that equality. I do have to say that if I did full intros, whatever. There's another tactic called destruct, and destruct is slightly smarter than case. And so in particular, it will look inside the hypothesis, and it will replace X by Monday in the right case. So I could have used destruct. Let's see. I'm not sure what behavior. James Gill asks, is there a tactic that applies a subtactic, resolving any goal that it can and leaving all other goals?
Sorry, maybe I could.
Yes, there is a tactic. There's a tactical called try, right? Where I could say, instead of this, I could just say try reflexivity. And that will just solve the ones that reflexivity solves. The problem here is that now I have the 42 goals, and there's no way from here on to do everything on the 42 goals. I would have to semicolon here. And here I can do, intros, H0. And now I have my 42 goals, and they're all of the same form, so I can do inversion H0. So this is actually how I do proofs. I'll do try, and then I'll look to see if the number has gone down, right? So the number did go down, right? Yes, Gregory, thanks. Sorry, I lied a little bit. I said there's no way to apply something to everything by default, but there is. Right. So this is kind of nice. So normally you don't want to do this all colon, or at least I feel like it's slightly an anti-pattern. Normally you want to do semicolon and then say all the sub-goals generated by this tactic, do that. And then semicolon, all the sub-goals of that thing, do that. And that way you kind of keep the tree structure of the proof. All right. So basically, oopsie daisy, every time. Basically, all right, so this was the first real proof. And like I said, all right, so now we have Monday equals Monday. And this is not a very exciting goal, but we can apply our newly found lemma excitingly. We can do apply second real lemma. And that says, okay, well, my second real lemma says Monday is equal to Monday if equal WD Monday returns true. But it turns out it does. If I do compute, that reduces to true. And now I can do reflexivity. Now this seems like a stupid way to prove Monday equals Monday. But you can imagine a much more complicated goal with a much more complicated proof. And if we had something like second real lemma that turned a complicated goal into just a computational problem, we could apply the lemma and then just do compute. And all this logical reasoning would have been subsumed by this lemma. plus a computation. All right, so that's a fundamental idea in Coq that actually doesn't really exist in Isabelle. And it's a powerful one too. It's a very powerful way of turning difficult, finicky proofs into computations that are all like subsumed by this big lemma, and then just run compute to do a computation. All right, I'm going to try and get through this part. I actually feel like I'm not going to have that much extra time. All right. Yeah, Greg says that I'm very inconsistent in the subtleties that I'm going to explain. I agree. All right, so speaking of subtleties, here is another inductive type, but it's actually an inductive predicate. All right, this fancy P is prop. And I'm defining a new logical connective. It turns out that and or are all defined in the standard library in this way. All right. So the inductive predicate, what does this say? It says, given a weekday and a weekday list, I'm going to define a new kind of specification, which is called mem. All right. So mem of a weekday and a weekday list is true if one of these two things is true. Either the weekday is W and the weekday list is const of W onto a list. All right. In which case mem W const WL holds. Or I already know that mem WL holds of some list. Then it holds of W and the same list on which I've const something else, right? So this is a long-winded way to say I am defining a logical concept of membership in a list. And being a member of a list is either I'm at the head of the list or I'm somewhere else inside the list, right? And you notice that I don't have any nil cases here because there is no way to be a member of the empty list. All right, so how do I prove this? Well, these two constructors are actually things I can apply, right? So if I want to prove that Monday is a member of the list Tuesday, Monday, Thursday, I can say, well, it's not at the head, so certainly I can't apply mem head. But what I can do is apply mem tail. Okay, and like I said, mem tail says that being a member of this list, it suffices, it's enough to know that I'm a member of the tail of the list. Okay, so I could apply mem tail again, but now I'd be stuck because definitely Monday is not in that list. So I've gone too far, but luckily I can apply mem head again. And this one works, and I'm done. All right. So I can leave this one to you guys. I'll just give you a minute. See if you can. Oh, sorry, I haven't done exists. Shit. All right. Existentials. How do you prove existentials? You basically have to give exists and then something, which is the thing you know to exist. So if you want to prove that something exists, you have to say what it is, the thing that exists. So I can say exists Monday, or I can say exists, Saturday. And now I have the old membership problem. So why don't you all try that? All right. So here I can do exists Tuesday. And then I'd like to see inside the work week. So I can do compute. That works. But I can also do unfold. Yet another command that acts kind of like compute in some situations. All right, and now I'm in the same situation as before, so I do apply mem tail and then apply mem head. Great. Phil's asking if I still have time to do my sort example. I definitely do not in 10 minutes. All right, so here's another thing that we probably want to be able to prove, right? Is that there exists a weekday that is not a work week, right? If I do unfold work week, you see that that's just Monday through Friday. So we sure like to be able to say that Saturday is not a member of the work week. However, this is actually quite hard to prove. All right. So negation is actually just a shorthand for implies false, right? So I can assume H and get false. And now I want somehow to get a contradiction out of the fact that Saturday is a member of this list. And this is actually finicky, right? This is there's no real way to do this. You can try case H, but that does not help at all. See, my first goal has just gotten just strictly worse. And so you're kind of stuck here, actually. So the trick I want to do here is build the same way I proved the correctness of equality. I want to prove the correctness of is a member. So the is a member function returns a Boolean, remember, if the weekday is if the weekday is part of the week list. Now I've built a predicate which expresses that fact as a specification. And now what I want to do is what I did earlier, which is show that that specification exactly corresponds to that program. All right. So this one is actually pretty easy. I can just do intros and then intro W, and then case W. And then, if I do compute, oopsie daisy, that's not good. Oh, sorry. Yeah, sorry. casing on W is not going to help. Oh yes, we need induction. Fantastic. All right, I forgot I had induction in this thing. All right, so we actually need induction. So what you want to do is reason by cases on the list, but you're going to need, you know, a base case, and because list refers to itself, you can actually do induction on L. So if you do case L, you're going to make some progress, right? Because if you do compute here, you're going to get false equals true, and you can do intro H, you know, inversion H. That's gonna handle your base case, right? If your list is empty, then certainly the theorem is true. But now in your cons case, if you do compute, you're gonna have a case where W is equal to W0, and then you're good, right? Because you can just say, okay, well, you know, mem W const W1, you know, I'm good because I can apply mem head. All right, but if I can't apply mem head, then I'm in big trouble because now I need to apply mem tail, and that's really, I mean, it's not helping me. I'm back in the same situation I was originally. I have to prove something of the form mem W and then some list. So I really do need induction here. Okay, now I have two cases. The first one is the same. I can do compute. Get false equals true implies something. Great. Now my second case is more interesting. My second case, I have my weekday, I have my W that's, you know, in, you know, where this computation returns true, but I also have an induction hypothesis, which says, okay, but if W is an L, I'm sorry, if is a member WL returns true, then definitely W is an L. Okay? And now I don't have quite that in my conclusion, but I have something close. And basically, I just need to just decide whether W0 is W. And if it is, then good. Now, compute is actually a little bit too much. There's another tactic that is, oh, nice. All right, in the comments, Stavros showed that this lemma can actually be proven with sufficient, you know, elbow juice. But I'm going to show the right way to prove it. All right, so is a member W const WL equals true? I can do simple here. And what I get here is, you know, equal WD WW0 or is a member WL equals true. All right. So one thing I just know for a fact is that will be equal to true if and only if one of those two things is true. All right. And we're kind of reaching the end of the time, which I guess I'm kind of glad we had all that time. And yeah, so I'm just going to kind of show you how to get through this, and then I'll just tease the remainder of the talk. So how do I show this? I can definitely do struct equal WD WW0. All right, again, I'm kind of using extra knowledge. Oh, wait, no, I don't want to do that. I want to do case QW. All right. So I'm going to reason by cases, but I still want to keep around the fact that I'm, I'm considering equal WD. All right. So in the case that equal WD, WW0 is true, I actually know that W and W0 are equal. And why do I know that? It's because I have the second real lemma here, right? So I proved that earlier. Oh, wait, sorry. I'm going to do a simple first. Wait, no, I don't care about that. Sorry. All right. So I have this hypothesis H, but I know that H implies something I want, which is W equals W0. So what I can do here is an assert, which creates a new goal, which I now have to prove. But this new goal is easy. It's just apply second real lemma, and then apply H. Great. And once I'm done with my new goal that was created by assert, I get to use it. It shows up here as H1. So now I can use H1, and I can just rewrite H1. And now I have mem W0 const W0L. I can just apply mem. And that works because W and W0 are exactly the same thing. Great. All right. But I have my other case where equal W0 is false. All right. And there, I mean, that doesn't help me at all. However, false or something is the something, which I can get by simple. All right. And that just says false or anything is the anything. Great. And now you see that this whole area here is almost exactly this. All right. The only little difference is this const. But it turns out that applying mem tail will exactly just remove the const. All right. So now I can do intros. Do apply mem tail. And now I get this. And now I can apply my induction hypothesis. And apply my induction hypothesis gives me exactly what I already know to be true, which is that is a member returns true. I can do apply H0, and we're done. All right. All right. We've already gone over, so time for the wrap up. All right. So is a member complete is kind of a similar proof, but you need to do induction on the fact that W is a member of L. It's actually somewhat easier, I think. But I'm not going to do it. I'm just going to do admit. TED. Admitted is something you shouldn't really do as much as possible. But it is a way of saying, OK, I know this is true. I don't have a proof. I'm just going to assume it for now. And now I'm going to do this lemma from earlier, which is going to become much easier. Basically, it's going to be the same thing as the trivial thing, which is I'm going to say exists Saturday. And I need to prove that. I'm going to do intros. I need to prove that. Oh, sorry, intro. And I want to get a contradiction from H. How do I do that? Well, I know that is a member of Saturday work week is false. And that's just trivial to prove, right? It's compute reflexivity. But I also know that is a member Saturday work week equals true. How do I know that? Well, that's because in my context, I have this. And I can use this lemma to turn the computational fact into the predicate fact. All right, so now I have something equals true. I have that same thing equals false. I want to deduce a falsehood. I can do rewrite H1 in H0. And then inversion H0. All right, so you see that that complicated negation is made easier by the use of this function plus these two lemmas. All right, I've gone over. I apologize. I think we should finish up. Thank you all so much for your attention, and I will see you in GatherTown.
All right, thank you, Cody, for an awesome tutorial. I think we've seen two very, very different parts of the formal verification landscape the last 2 days. It'll be a great lead into the symposium tomorrow. So if this were an in-person event, I would say let's give Cody a big round of applause. And then would love to continue the conversations more generally in the Gather space.
Thanks. And Gopal, you know, I hope I'll have the opportunity to see us tomorrow, but thank you so much for organizing. It's really great what you've done.
Absolutely. It's been my pleasure.